The question of how everything came to be has perplexed humanity for millennia. Philosophers, theologians, and scientists have devised intricate cosmogonies, each attempting to forge a causal chain leading from some fundamental essence to the structured reality we observe. Every myth, whether religious or scientific, feels compelled to justify existence through a process, a sequence of transformations from an initial state to the complexity we witness. Even in physics, with its relentless quest for a unified theory, the question of how remains central, demanding an account of causation, emergence, and transformation over time. However, there exists a unique alternative that entirely sidesteps the need for such a how, the proposition that reality is mathematics. If everything is fundamentally mathematical, then reality requires no creation story, no sequence of events leading to its present state. Mathematics simply is. Consider a triangle. Its properties and existence are self-evident within the logical framework of geometry. It requires no external cause, no deeper justification beyond its definition. The same applies to numbers. 0 simply is, and from it, the entire edifice of mathematics follows logically. 1 emerges from 0, then 2, and so on, extending infinitely through integers, rationals, irrationals, reals, and complex numbers. Every mathematical object exists by necessity, embedded timelessly within the logical structure of mathematics itself, demanding no causal mechanism to bring it into being. This emergence of complexity within mathematics is fundamentally different from that proposed by any other cosmogony. In every myth, even those of modern science, the foundational essence, be it a deity, primordial chaos, or a quantum vacuum, must undergo a process, a transformation, to generate the rest of reality. This invariably invites the question of why such a process occurred, what initiated it, and why reality unfolded into the specific form it possesses. But if reality is mathematics, no such explanation is needed. There is no moment of creation, no divine intervention, no initial event, only the timeless existence of mathematical structures. If everything is mathematics, then how it came to be is not a meaningful question. Reality need not have come from somewhere. It simply is, as self-existent and necessary as any number or geometric form. Intriguingly, our deepest explorations of the physical world lend credence to this seemingly abstract perspective. The very concreteness of stuff, the solidity we intuitively assign to reality, has significantly diminished under scientific scrutiny, revealing a world far closer to abstraction. What we first identified as solid matter became ever more rarefied. We learned it consists mostly of empty space, shattering the notion of indivisible atoms like tiny balls. Further investigation revealed that the residual matter occupying the voids behaves, at least partially, as waves, fluctuations in immaterial fields. Pushing deeper with high-energy collisions painted an even more abstract picture. The fundamental constituents, quarks, don't account for the bulk of the mass in the particles they form, like protons and neutrons. Much of what we perceive as substance arises from the energy of their self-interactions at light speed. Moreover, these quarks cannot even exist independently. They are perpetually confined within composite structures, pairs in mesons, triplets in baryons, never observed alone. Compounding this retreat from solidity is the realization that the familiar matter, the kind we can taste, see, touch, and smell, is cosmically anomalous, representing a mere 5% of the universe's known energy content. Around 25% is attributed to dark matter, an unknown substance whose presence is inferred gravitationally but which, if composed of particles, likely flows through us undetected. The remaining 70% is ascribed to dark energy, an even more mysterious component driving cosmic acceleration, whose fundamental nature remains entirely unknown. Given this profoundly abstract picture painted by physics, the notion that reality might be fundamentally immaterial, akin to music, dreams, ideas, or mathematical structures, appears less radical. Among these possibilities, mathematics holds a distinct advantage: its inherent logical consistency, which can be rigorously verified and explored. Simultaneously, our understanding of mathematics itself has evolved dramatically. With the advent of areas like fractal geometry, mathematics has demonstrated its capacity to describe the inherent roughness, complexity, and intricate detail observed in the natural world. It no longer seems merely an idealized approximation of physical reality. Rather, mathematical structures exhibit a richness and complexity that can encompass, and perhaps even surpass, what we directly observe. Consequently, the old adage that the map is not the territory begins to lose its footing. When the territory, physical reality, appears increasingly abstract and relational, and the map, mathematics, demonstrates the capacity to embody such complexity intrinsically, the distinction blurs. It suggests a more profound relationship. Perhaps the territory is a mathematical structure. This brings us to the second fundamental question. Why mathematics? Why should this abstract framework be the essence of reality? The answer lies at the heart of mathematical realism, a philosophical stance with roots tracing back to the Pythagoreans, yet entirely compatible with modern scientific rigor. If reality is mathematics, we immediately understand why mathematical structures underpin all observable phenomena. It explains why formulating a physical process mathematically allows for precise predictions, why Newton's equations could chart the paths of planets he'd never see, why Maxwell's equations anticipated the existence of electromagnetic waves before they were generated or detected, and why Schrödinger's equation successfully governs the strange behaviors of the quantum realm. More astonishingly, mathematical realism illuminates why abstract constructs, sometimes introduced purely for the internal consistency or elegance of a physical theory, often turn out to correspond to tangible aspects of reality. Theoretical physicists conceived the mathematics describing certain mesons before experimentalists discovered them. The Higgs field was postulated based on mathematical symmetries needed within the Standard Model long before the Large Hadron Collider provided evidence for its existence. Even the cosmological constant, initially inserted by Einstein as a mathematical fudge factor and later retracted, has re-emerged as potentially representing the very real dark energy dominating the cosmos. Outside the framework of mathematical realism, these remarkable correspondences between abstract thought and physical discovery often appear as inexplicable coincidences or unreasonable effectiveness. Why should purely mathematical reasoning, often pursued for its own sake, lead to verifiable truths about the physical world? No truly satisfactory answer exists if mathematics is considered merely a human invention or a descriptive tool. But if reality is fundamentally mathematical, then this predictive power is not mysterious at all. It is a natural consequence of discovering the inherent properties of the mathematical structures that constitute reality itself. Thus, mathematical realism transcends being merely a philosophical preference. It presents itself as perhaps the most coherent and parsimonious foundational narrative available. Unlike other worldviews, it does not necessitate ad hoc explanations for its effectiveness, invoke supernatural interventions, or even rely on conventional notions of temporal causation for reality's fundamental existence. It stands as the framework that allows reality to simply be, without requiring external justification or a preceding cause. In doing so, it offers the most elegant answer to both how and why everything appears to be mathematics. Because, at the deepest level, there might be no fundamental distinction between existence and mathematical structure. Outside the framework of mathematical realism, these remarkable correspondences between abstract thought and physical discovery often appear as inexplicable coincidences or unreasonable effectiveness. Why should purely mathematical reasoning, often pursued for its own sake, lead to verifiable truths about the physical world? No truly satisfactory answer exists if mathematics is considered merely a human invention or a descriptive tool. But if reality is fundamentally mathematical, then this predictive power is not mysterious at all. It is a natural consequence of discovering the inherent properties of the mathematical structures that constitute reality itself. Thus, mathematical realism transcends being merely a philosophical preference. It presents itself as perhaps the most coherent and parsimonious foundational narrative available. Unlike other worldviews, it does not necessitate ad hoc explanations for its effectiveness, invoke supernatural interventions, or even rely on conventional notions of temporal causation for reality's fundamental existence. It stands as the framework that allows reality to simply be, without requiring external justification or a preceding cause. In doing so, it offers the most elegant answer to both how and why everything appears to be mathematics. Because, at the deepest level, there might be no fundamental distinction between existence and mathematical structure.